let me pick up where we were. We were at the end of the H2 molecule discussion. So we were here. We discussed extending the H2 plus discussion to H2, which is difficult, but pictorially or conceptually is the same. So we have this molecular orbitals formed by LCAO. So this two you may think as linear combining of one S on the right side atom and one S on the left side atom. Thereby, you will have two MOs. Remember the 2 by 2 matrix stuff? Two things in, you get two eigenvalues out. So it must be the case. So there is a lower one. That's nice. And then we count how many electrons we have. We have 2 electrons. The Pauli exclusion principle says we can do this. And thereby, immediately you see, you gain some energy relative to separate neutral atoms. Therefore, H2 molecules exist. And by doing so, some energy is gained. To quantify what is a bond, there is an idea of bond order. So this is the first concept. It's very simple, it's counting. The definition is, you count how many electrons are in the bonding molecular orbitals and how many are in the anti-bonding molecular orbitals. And then, since each bond is shared by 2 atoms, you divide it by 2. Okay, so it's a number divided by 2. So look at this H2. This is a bonding molecular orbitals. This is an anti-bonding one. This is a bonding one relative to the 2SAO atomic orbitals. This is an anti-bonding one. Well, nonetheless, they are all empty except the lowest one. So we have 2 electrons in bonding, MO, 0 in anti-bonding. So we have 2 minus 0, and then shared by 2 atoms. Therefore, everybody knows this answer. So H2 has a single bond. But now you have a quantified definition of how many bonds are there for this molecule. Okay, so this is, I believe, another step forward in your understanding of how things bind in nature. That takes us back to H2 plus, molecular iron. So what is the bond order there? Interestingly, if you count how many electrons you have, you only have 1. So that goes into the bonding orbital. And then, therefore, you have 1 minus 0 divided by 2 atoms. So H2 plus formally doesn't have 1 bond. It only has half a bond. And that is the formal quantified number for that bond. And you must have heard beyond single bond, there are things called double bond or triple bond. It means the bond order is 2 and 3 respectively. We will look into how we could have 2 bonds. Therefore, it means we have 4 electrons in net 4 electrons in bonding MOs. Then you divide it by 2, there will be double bond. At this point, I just want to point out that in addition to a sigma bond, all this double, triple bond will have some other type of bond that we call pi bonds. So that leads us to the discussion of further LCAO using P state. For S state, a S is a ball, another S is a ball. You add it, you subtract them. The whole thing is like a peanut at the end. It is always rotational, symmetrical along the line joining the two nuclei, thereby S always form a sigma bond. Thereby, when we want to understand how come we have double bond, we must go into bonding by p atomic states. And that is what we want to discuss. So the next thing is that we extend our discussion to p. So I have a p. Remember, p is like a dumbbell and letter 8 shape atomic orbitals. So it has to do with plotting out the YLM theta phi for L equals 1. The Y10, L equals 1 is P, then you have ML being 1, 0, minus 1. The Y10 is automatically pointing to the Z direction like this dumbbell. So this is the PZ. But for PXPY, we call that we need to linear combine them to form, linear combine Y11, Y1 minus 1 in order to form real P state. Now, these are complex spherical harmonics, but if you do this combination, I think I may have missed some I here. Let me see. That's fine. Okay. So then you will get the PX and PY. Okay. So these are directional. The S is non-directional. It's a ball. Okay. Thereby, we started to have this sense of maybe two P's, a P here, another P here, pointing at each other. Then the end result is a longer peanut. It still has this rotational symmetry. Thereby, there will be a PP sigma. However, I could have a P and another P like this, and they just overlap slightly, but all the electron density will be concentrated vertically. Thereby, you don't have this rotational symmetry anymore. You rotate it, the electron density vanishes. Okay, so that will be a PP pi. Okay, so that's the whole picture, and let's move on to look carefully into these scenarios. So here is a key concept that I already mentioned, but worth remembering in understanding molecules. For isolated atom alone, an A, it has no sense of direction. It doesn't know what is X, what is Y, what is Z, okay? And when we solve an atomic problem, we use R theta phi, X, Y, Z. It is our mathematical convenience. We could define any X, Y, Z and then start doing that. But for the atom, it doesn't have any sense about what is X, what is Y, what is Z. The space is isotropic, okay, for a lonely atom. However, when there is an other atom around, thinking about forming a bond or not, then naturally there will be one direction that is special. That is the direction joining the two atoms or the nuclei of the two atoms. Okay, once you have a special direction, then we can call it X or Y or Z, but it is a special direction. And it is this direction with respect to which we will consider whether when we rotate the charge distribution of the electrons around this direction, so we have a direction, the axis of rotation, that is, we could rotate it and see whether the charge distribution has this symmetry, okay? If it does, it is sigma. If it doesn't, it is pi. That's it. So with this idea, the PP bonding becomes more interesting than SS. SS can only form sigma bond. Okay, because circle, a ball and a ball, whatever you form, it has this rotational symmetry. Okay, but PP, there will be more possibilities. Let's see. Obviously, I could have a P and a P. Okay, so I'm forming LCAO of this P. I call it PZ, and this PZ. Just like the SS, I could have two linear combinations, a plus and a minus. So the plus one will have this positive loop happening at the same place. So you add them up, there will be an enhanced probability of finding the electrons in the middle between the two nuclei. Obviously, that will be a bonding state. The electron here will have a better K integral. So it is quantum stuff, okay? But in your high school language, it says the electrons live more here, can enjoy the benefit of the Coulomb attraction from A and from B. So more stable, okay? So that is the J part, the J integral part, okay? But this is the bonding state. It gains energy by doing so, lower the energy. The minus linear combination has a nodal plan in the middle because they subtract each other exactly at the midpoint, okay? So you see there is a 0 point in the middle, okay? And if you extend it to three-dimensional, the whole plan cutting through the midpoint is a 0 plan, okay? That is called a nodal plan, okay? Now, that is bonding and anti-bonding when they point to each other. But now, how about sigma or pi? Now, both of them are sigma for the following reason. Put an axis here, you rotate this, whatever angle you rotate it, the charge distribution of the electrons, the probability, the wave function square, okay, looks the same. It doesn't matter which angle you rotate it, okay? It is the same symmetry even for the anti-bonding state because they point to each other, all right? So therefore, we have multiple description. Pay attention. This is bonding. This is anti-bonding. So the energy of bonding is lowered. Anti-bonding is pushed up, all right? But both are sigma. So this is sigma PP. This is also PP sigma. To distinguish, just a notation that this is bonding, this is anti-bonding, we put a star in the anti-bonding state. So in summary, we have this PP sigma star, all right? But we have other P states, right? In addition to the PZ, we will have PX, PY in other directions. So after we call this Z, there will be X direction and Y direction, which is lying on the plan, okay? Now, look at the X direction. We will have linear combinations, add them or subtract them. Subtract them means minus the second one, so you just flip the sign of the wave function. Okay, and then add them together. The picture of adding them together is that you have this dumbbell shape on the left, on the right. You add the wave function together and then take a square. Okay, now immediately you see this overlap concentrate in this vertical direction, okay, there's nothing here. It all focus vertically, okay? That is to say, if you rotate along that axis, it goes from very strong number, the electrons are here, to nothing here, okay? Therefore, you don't have the rotational symmetry, and this is pi bond. This is to go with against a sigma bond, okay? Sigma bond has the rotational symmetry, pi bond doesn't. So this is pp pi, all right? Now to be more specific, it is px pi, but the py pi is the same by symmetry. So we also have anti-bonding pp pi because I flip the sign and then it will subtract each other. This is, again, in the midpoint, there's a plan. There is a plan here that is 0. Again, it's a nodal plan. This is the signature of an anti-bonding state, okay? This subtraction of two wave functions. So in a picture, we have px, atomic state, px atomic state. They form the 2x2 matrix, push each other up and down, forming a bonding pp pi and an anti-bonding pp pi that I call pi star, all right? So it is with this picture that we could kind of have this general sense of what happened when two atoms comes together, each carry a px, py, follow my cross, and pz, okay? Here we separate the discussion, but an atom carry pz, px, py at the same time, all right? So now, here I show that there is a atom A, atom B, each with this px, py, pz. So what happened? Now, formally, we should form a 6x6 matrix to handle it, right? Because it is linear combination of 6 atomic orbitals, 3 from each atom. That's fine. At the end, we will get 6 PMO, right? 6 in, 6 out. Following our discussion, there will be a PP sigma. So we will have 1, 2, and then we will have 3, 4 in the X, and then 5 and 6 in the Y. So 6 in, 6 out, that is the situation. So this is what we try to depict here. Okay, now we only see four energies, but because of just symmetry consideration, the pi one will be the same, because what you call X, I will call Y is the same. But Z is a very special direction. That is the direction joining the two nuclei. On the same figure, I also show you the other lower energy, deeper MOs. The atom, of course, has a 1s. So this 1s, like a ball, can also overlap with the other 1s and forming this 1s bonding, 1s anti-bonding. Also, it has a 2s, so it's 2s bonding, anti-bonding, all right? However, for simple chemistry consideration, if those 1s are filled, completely filled in atom A and atom B, there's no room for doing bonding of the two atoms. Its own electrons already completely filled that 1s, okay? That's one point. So the chemistry will not involve them. Second, if you have the p states ready for bonding, that is to say, there is one electron in a p orbital in an atom waiting for the other electron in the other p state on the second atom. You have a pair of electrons waiting to form bond. Then the 1s, being a deeper atomic state, the wave function will decay faster to 0 than the p. The 2p will be extended further outward, all right? Therefore, when you do LCAO, all it has to do with how strong this overlap is between the atomic states of different atoms, right? So the 1s will only touch each other slightly, okay? So therefore, if there is something that atom A feels the presence of atom B, it must be the outermost partially fielded atomic orbitals. Therefore, those deeper states usually will not matter much. Nonetheless, here is a schematic diagram. The x-axis is the separation between the two nuclei, okay? If they are farther away, nothing will touch each other. So the atomic state will remain atomic state value. That is this limit, okay? Only when they come to each other closer, then we have this 2x2 matrix or 6x6 matrix with the off-diagonal elements start to be finite. And those will push each other by perturbation theory. And that's the idea. So here is one picture for 3 molecules, NO, N2, O2, and fluorine, so F2. Let's start with N2, okay? Now, here we have the lineup for 2s sigma sigma, sigma sigma star. So these two states is the 2s bonding, SS bonding, SS anti-bonding. And then we have this 6th state from the 2p. Notice that it is a quantum mechanical calculation result. Each molecule is a separate problem. Thereby, you even see that the line up, the alignment of the energies are different from N2 to O2 to F2. You do not have a one-size-fits-all spectrum, okay? Here, I also show you how the electrons are filled up. For N2, we have 6 electrons to fill the p orbitals, the PMOs. So we can fill all the bonding states. And there is no electron in the anti-bonding PPMOs. So we count how many are in the bonding. The lazy way is don't count the completely filled ones because they will cancel off, right? This sigma, this SS sigma, so deep. You have 2 electrons here, 2 electrons here, 2 minus 2 will be 0. So all this 1s, 2s, they cancel the bond order number to 0. All we need to care is this PPMOs. So we have 6 electrons in bonding MOs, 0 in anti-bonding. So we have 6 minus 0 and divided by 2. Therefore, it is a bond order 3. And the name for that is a triple bond. Okay? But now we have a deeper understanding. For this triple bond, 1 is sigma. Only 1 is sigma. And it is P sigma. Okay. The other two are P pi bonds. Okay, naturally. And I hope now you have a better understanding of this all this thing you should have encountered in your chemistry course, but now it is quantum mechanics backing it up. So for O2, we have two more electrons, and by Hund's rule, we better fill it with this spin aligned. That will be the lower energy way to fill it, but that is a separate story. That is about the Hund's rule. Nonetheless, for the bond order, it doesn't matter. Now we have 6 electrons in the p bonding. We have 2 in the anti-bonding. There will be a net 6 minus 2, 4 electrons in bonding MO divided by 2. The bond order is 2. That is a double bond. And then we know what is this bonding nature. There will be a pp sigma, and there's this one pp pi. Okay. And for fluorine, the same story goes. You have 2 more electrons in the antibonding state, and therefore the net in bonding is just 2. Divided by 2, you only have a bond order 1. It is a single bond. So that is the story about bonding, still same kind of atoms. The next 2 pages is just a remark, just to warn you that we have a good theory, Nobel Prize winning LCAO-MO, but nonetheless, it gives, I think, 95% of the picture, right? Why don't we have, say, S and P orbital bonds? We will do that later, all right? We will have SP, okay? That will have to be the case. When the left atom has 1 electron in S, okay? And the right atom has a lonely has an electron unpaired in a p state. Follow me? All right. Then that will be the kind of molecule that the 2 atoms will be different. Do you see? Okay. We haven't got to that point, but soon, real soon. Okay. So now. Here, the purpose of this page and the next is just to warn you that LCAO-MO, very nice, Nobel Prize winning, yet it is an approximation. Sometimes we need a full quantum mechanical Schrödinger equation solution in order to understand something that is more fancy, okay? So here is a very strange example. Scientists has been trying to find the weakest bond. That is to say, the bonding well, the gain in energy is just a little bit, okay? So what is this weakest bond? It is helium-helium. All right. Now you may think helium-helium should not bond, right? Because we have 4 electrons, 2 in the bonding, 2 in the anti-bonding, and then you gain something, you lose something, maybe there's no net, all right? Simple picture. And that is mostly true, and I think you can take it as the truth. But still, very fancy experiment has been done, and then it was found, for example, I give you this abstract of a paper in a good journal. It says that they found evidence for the following thing. There is a helium-2 molecule but look at this first. The bond length is 60 angstrom, so very far away. Okay, so whether you take it as binded or unbinded, I think is arguable. The binding energy, how much it was gained for this, forming this very far away, loosely attracting each other bonding, it is just 0.01 joule per mole. To give you an order, if you change it to a temperature, it is millikelvin. Okay, that is to say, at any reasonable temperature, that is already sufficient to dissociate this helium to two helium atoms. Nonetheless, it was experimentally studied. And then they are not, that group was not the only one. So after several years, another paper in Physical Review Letters, another good journal, further confirmed that, and the numbers are around the same ballpark. So the bond length is 52 angstrom, so it's still very long, and the energy, binding energy, is still in the millikelvin range. So it is that weak. Okay, so my goal here is, you believe what quantum mechanics says? Well, all this follow the Schrodinger equation, but when we make approximations such as Born-Oppenheimer and then LCAO-MO, use the results with cautions. That's the story. And now it is to answer Mr. Poon's question, okay? Why don't we have SP sigma? The answer is yes, we have SP sigma, okay? But as already mentioned, in this case, we need to consider the molecules of the type of different atoms. So it is an A atom and a B atom. They are different. An example is this HF. And this week, there is a sample question that the TA will work out some numbers for this particular case. Here, I just give you the picture, okay, without the exact numbers. So for H simple, we have one electron waiting to bond in the 1s, that is the ground state of hydrogen. So the S will donate something that is a ball, a sphere, okay, S state. But fluorine, the atomic electron configuration is 2p5. So among the p state, you have 5 electrons. So you will have 2px2. The px has 2 electrons, py has 2 electrons, pz has a lonely electron. And that it is that electron that is waiting to form a bond with the hydrogen electron in the 1s. That is to say, we will encounter sp sigma. Okay? It is easy to think that it is a sigma bond because you can think that H is a ball, the F is like an A shape 8. They touch each other, it forms a very strange type of peanut. Nonetheless, you rotate along that axis, you have this rotational symmetry. Okay? To put your mind into a simpler picture, you can think of this type of things as 1D analogy. A atom is a well, B atom is also a well, but since they are different, maybe one is deeper or shallower, it doesn't matter, they are not the same. Now they come together to form a molecule. You can think about it as this, okay, or that kind of problem. Now, even without doing any calculation, if someone asks you to draw the ground state of this problem, you think like a physicist, right? This is deeper, lower potential energy. The wave function should tilt to this side more, right? Should have a bigger part on this side than this part. So I exercise this sense. I just sketch roughly what I think about of it as the ground state wave function for this 1D problem, okay? And you see, you will have more chance to find the electrons on one well than the other. You don't have the symmetry when the wells are identical, okay? Interpreting this as the electron probability, that gives us ionic character, right? The electron will be more to go to one side than the other. They start with being neutral atoms. And if the electrons on this side want to go to the other side, the fluorine will become a fluorine minus, right? And that is ionic bond, what you call ionic bond at the end. But for quantum mechanical sense, it is just the result of a quantum mechanical calculation. So when you have this situation, immediately you can think about it as the following. The simplest LCAO will be fluorine A2P, all the other are completely filled. They will not engage in chemistry. The H gives the 1s. So I have two things forming a linear combination, hopefully forming two MOs for me. This is the MO. So I set up the variational calculation. There will be a 2x2 matrix problem. Okay, I solve the determinant equals 0. I will get the push down and push up the bonding, anti-bonding state. Okay, so now you may even go further. What is this H11? If I call this 1, call this 2, H11 should be something like H1s on the left, H1s on the right. You have the full molecule Hamiltonian. Nonetheless, since the two atomic states are the hydrogen 1s, it will sense the part of the seeing the hydrogen nuclei more. So roughly speaking, that is a good approximation, that H11 refers to the atomic energy for the hydrogen on the left-hand side. Similarly, H22, because both 2 refer to the fluorine P. So H22 is like the fluorine atomic energy for the 2p state. Okay, now this is minus 13.6. This is slightly deeper because fluorine, the nucleus is more positively charged, stronger attraction for all the electron. So the atomic levels are lower in energy than hydrogen. Okay, then how about the other things? Now I'm doing some very dirty physics here, but works. How about S11 is 1 because atomic hydrogen normalized. S22, 1, okay? How about S12, okay? Now, you have an atomic hydrogen, you have a fluorine P. Formally, S12 is a function of the separation between the two atoms. Okay, that is formal. Okay. However, if our aim is just to solve for the roughly the eigenvalue, it is not a bad approximation to simply say S12 is 0. They touch each other, all right, but they touch each other slightly. So I want to make this approximation because the matrix will become easy to solve. Okay, so let's say it is the case, then let's see what happens. All right, so I will say this is 0, and then I represent this by delta just to make sure that you can make connection to your homework problem number 1. So I will have a problem like this at the end. So let me repeat the physical sense. You have a hydrogen 1s, okay, like a ball, you have a fluorine P, okay? So-called, this is number 1, this is number 2 in my notation. So 1, 1. It is very much like the business of the hydrogen atom alone. So I would say it is minus 13.6 eV, okay? And that's what I call epsilon 1s. Similarly, H22 is the fluorine business. I will call it epsilon 2p for fluorine. I think it is minus 18 eV or something, deep by 5 eV deeper, okay? And now what I'm saying is that for the wave function alone, they touch only very weakly in the middle, okay? So I will ignore that and I will make this S12, S21 equals 0. The only thing that matter here is the following. I have an integral, I don't know the number, but I know that matters. That is the full Hamiltonian, hydrogen 1s, and fluorine 2p, and integrate over all space. Okay? I don't know what it is, but in notation, this is called H12, okay? And H12, I give it a new notation to make connection to your previous work. I call it delta star. So it is this thing. Thereby, H21 will be the delta. The whole problem simplifies to a very familiar matrix problem, okay? And that is the way to think about bonding, that's the point. So here everybody knows how to solve this, okay? By perturbation or even exactly, we know that the higher one, so the hydrogen, will be slightly pushed up, okay? You even know the amount, right? I hope. This amount will be delta squared divided by the energy difference. This is perturbation theory, right? Okay? And you know, given this is something like 5 eV, this push will be tiny. So I draw it just as a small difference here to illustrate the point. Similarly, the fluorine side will be pushed down by a little bit, actually by the same amount. Okay, you flip the two energy, that will be minus, that is going down. Okay, so you see, indeed, it will form a bonding MO and a anti-bonding MO. Okay, and the picture is that I have a ball add to an 8. It will form a funny peanut, and that is actually a sigma bond. We rotate it, okay? It's still symmetric for all angle of rotation. Now filling in the electrons, I only have 2 electrons, one from hydrogen, one from the lonely 2p. So that will occupy the bonding. At the end, you see some energy gained. All right, that's nice. And then you will have sp sigma bond. In addition, because you only have this kind of matrix problem for this eigenvalue, this MO has a strong fraction or linear combination of the fluorine 2p state. Okay, remember by matrix mathematics, the one that is closer in eigenenergy to this, the linear combination will have, say, 85% of this 15% of that. So that will carry a high percentage of the fluorine atomic orbitals. Okay, so the picture now becomes what is ionic bond. The linear combination will have a big weighting of the fluorine P and a small weighting of the 1s hydrogen. So 2 electrons occupy this state. Okay, you multiply the whole thing out, you will have 4 terms, but there is one dominating term because that is a big coefficient. You multiply into it, electron 1 will be in 4 2p, electron 2 will be in 4 2p. You have more chance to find both electrons on the fluorine side. That is forming a fluorine minus ion. Okay? Therefore, at this point, you don't need to remember or memorize things. This ionic covalent thing is not something to remember. It is a consequence of quantum mechanics calculation. It is the end result. In quantum mechanics, we only get the wave function. That's it. How the wave function distribute the electrons, then we look at the picture and then see there is some strong ionic character in this bonding. And this is the case for HF. Okay? Some remark, okay? So we only consider the 2PeZ of fluorine. You may ask, what happened if I include the fluorine 1s, 2s, and all the other things? That's fine. You can do it. The matrix will be bigger. Then you will have more electrons to fill in. At the end, what matters, the dominating physics is still has to do with 2p of fluorine and the 1s of hydrogen. Although you have included more of that in the fluorine, it doesn't matter, okay? That will be more accurate in principle, but it will be more complicated, okay? So at this point, I have to follow the university's guideline. I will give you 10 minutes till 10:32. Do you receive a link from the university for the course evaluation? It's an email. Do you have that? Okay. According to the university guideline, I should give you a few minutes